Right, I'm Adam Hahn. This is Nick Urlaub. We'll talk today about success starts with failure, mitigating OT security risks using threat-informed failure scenarios. So as previously mentioned, we work on the attack for ICS framework, which is a knowledge base of adversary attacks and techniques we've seen in the ICS sector. We've been working on this since it's been released about a little over 2 years now. We're seeing a lot of adoption. We're seeing a lot of great use by industry. This being incorporated to a lot of products, being used to better inform people about threat intel that we're seeing in the industry, especially across both a lot of industry products, platforms, and also by the government. Like we see recent like CISA reports mapping threats to attack for ICS TTPs. So it's really great. It's really enjoyable to work on a project that has such broad use. One question we hear often more from asset owners and integrators is, well, how do we use this? Oftentimes, they'll see we want to use this and use this to improve our defenses, how we detect for threats in our systems. But often maybe we don't see threats that really target our specific systems, our platforms, our sectors in this. And so they're really understanding how do we use this? Is there a way that a methodology we can use to start using this to improve our security? So that's kind of we've been going through this process of defining these threat-informed failure scenarios. Really what these are is just a set of cyber attack scenarios, TTPs, that are really tailored to your organizational process and architecture. So, when we do this, often what we try to do is understand what is an operational failure that's really unique to that system or sector. What's really the hazards you try to face, whether it's a safety hazard or some outage that can cause impact to your business or the public at large. What's really the thing that you really worry about, and then once we identify those, you can use the knowledge, the TTPs we've already defined in an attack for ICS, and understand kind of how an adversary could potentially disrupt your organization by tailoring those tactics to what's unique about your process and your technologies. And kind of once that's already identified, looking at what you can do from a mitigations or improve how you can improve your security operations to better be prepared for those threats and respond to those if you see them. And so the idea is, we think going through this methodology and understanding these techniques beforehand to happen has a lot of applications. One, it can help better assess and inform risk. So you can understand that we know that these are the techniques that we're most worried about that we need to better protect. And it can also help you communicate those risks to more a C-suite, where you say, hey, these are techniques we know have happened in other sectors that maybe we need to be worried about as well. You can look at what do we need to do to detect these techniques if they happen in these systems, or what can we do to implement mitigations. We previously provided mitigations in a previous release of attack for ICS. How can you protect those against those techniques? And so you can use this to better inform and guide how you maybe adopt those. I can use this to determine, what devices in your architecture you might want to test more, or what kind of, how do you want to scope some additional security testing. You can be more prepared for threat intelligence. So when you get the newest threat report, for an example, this is like the in-controller pipe dream malware. This came out with great to see these specific attack for ICS TTPs mapped in there. But I think many organizations aren't really prepared to say well, are those concerning to us, or do we need to worry about these, or are these going to be just not technologies we use or techniques that would be impactful in our operation? We can use those to better inform how to do security operations, understanding how SOCs are developing analytics, making sure you have kind of those analytics to detect those or workflows and can test those using some sort of adversary emulation. Or at a higher level, it could be used more for tabletop exercises, just walking through those, understanding how you respond to those techniques and TTPs if in those broader scenarios, if they did exist. So there's been a lot of, and I realize this slide's a little bit of an eyesore, but I just want to kind of broadly discuss this because there's been a lot of really great work going on about how we can better engineer security and risk into this ICS systems. And so there's a lot of great work by the CC at INL trying to look at how we do better end-to-end security protections. There's processes like the security PHA review, which really look at how do we extend what's going on in the PHA to understand whether cyber risk that could cause an operational hazard. There's kind of more theoretic approaches like the STPA work, SEC work that looks at like kind of system theoretics analysis of processes and understand what the hazards are. And I think our work just nicely complements some of these. So because we were really looking at, we had this knowledge of adversary behaviors, TTPs. How can we use these to understand exactly what the threat is or what's going to be more likely in your environment and inform kind of, how these hazards could occur. And then how can we use the work on the kind of mitigations and such to inform that? And so, a lot of these things like CCE has a lot of great discussion on how to do like consequence evaluation and scoring. PHA has work on, how do you identify where the cyber dependencies are with extending what's in a PHA or HAZOPs, and understanding, where that cyber risk might be able to cause some of those hazards. SCPA looks at like how do you enumerate the kind of hazards from like a systematic analysis. Well, so all these kind of really inform like what a hazard would be, and that's something that when we do these scenarios, we want to understand where those hazards come from. We're not really trying to understand provide a methodology to directly identify those. But once you kind of do know what that hazard is, we can look at the attack techniques and TTPs we already model, and you can look at how we might align them to those unique systems and understand which ones might be likely to cause those hazards, which one would be needed by an adversary to cause those. And so this is just kind of the where I think we contribute and can provide guidance on how to better identify the threats in these other approaches. And then similarly, from a defensive perspective, a lot of these look at how do we implement mitigations, protect the systems, how do we reduce our digital dependencies, and so a lot of the techniques mitigations we provide can specifically say like, well, if these techniques are relevant, we have mitigations that identify them or can protect against them. And then similarly, this is broadly used for not just like implementing mitigations, but informing your security operations too. So understanding how you respond to that, how you need to coordinate and resolve a threat if you observe it.
Yeah, so just wanted to take a quick second here and explain a little bit from one of the case studies that we're going to kind of wrap into this discussion about this approach, especially since this is an area that's not as well discussed. So, one of the places we kind of fleshed out some of this was with some work in the rail sector, looking at signaling and switching, or interlocking is another term for that. So kind of the big takeaways here, more or less kind of your standard SCADA-ish architecture distributed over a large area. You've got a control center in the dispatch center, and you have signal bungalows, which are kind of equivalent to substations in the sense that they're small, located sites out on the field. In this case here, we've got this vital signal controller, which is kind of the central piece for the system here, actually managing the signaling and interlocking. Again, signaling is the lights alongside the track that can tell the conductors on the train whether they should proceed or not, whether it's safe, need to slow down, etc. Trains are heavy, can't really operate them solely on line of sight. Interlocking is just the arrangement of switches in the rail space that you make sure that a train isn't going to collide with another train, or you don't swap signaling in such a way or switching in such a way that's unsafe. The other piece there is most of that stuff is directly wired into the vital signal controller, and the other piece for this is the vital signal controller is actually kind of the enforcement place for safety. So commands coming down from dispatch are always requests, not commands. So the vital signal controller is kind of the stop for safety there. So kind of fitting back into the approach discussion here. So as I'm kind of mentioned, the first place we start is kind of what failures are you concerned with in the system here? And as any time you're talking about some sort of operational environment, the first question is understanding how that system is set up. Always trying to understand like shared understanding here. Sit down with the actual operational folks. Have this discussion about what are they concerned with here, which kind of pivots into that first, or I guess the last category on the attack for ICS matrix impact. So kind of question, what impacts are we concerned with here? Is it damage to property? Is it loss of intellectual property? Is it loss of control? There's a whole host of those that are enumerated there. And that kind of starts to give you some idea of where you should start looking for potential hazards and failures that might be able to cause that impact. You can dig through HAZOPs, PHA results on that. it's safety incident report databases are a good source there, and there's a whole host of stuff, from NTSB reports, various ones for chemical accidents. So there's a whole host of those you can kind of dig through to kind of get a feel for what the actual safety incidents are concerned with. You may maintain one with the actual organization you're working with. FAMAs are a good source for some of the stuff as well, and just business continuity plans and their source for some of the more traditional IT consequences you might be concerned with. So once you've kind of established what you're actually concerned with as far as failures are, you can start to kind of figure out, okay, is this something that's actually cyber inducible? So you kind of pivot back to the question of, is there a device that could be the source of this issue, communication device, controller or something embedded in a piece of equipment? The also question is there data that could lead to this issue here? Telemetry, real-time commands, configuration application data. These all can lead to potential control failures if they're manipulated here, which kind of tells you that this is potentially cyber inducible, which in our rail case here, as I mentioned here, the vital signal controller is kind of that central point for safety here, which is kind of what we ended up targeting, this loss of safety. We did dig through a decent number of FRA accident reports. Federal Railroad Administration maintains a pretty robust accident report database here that the railroads have to report into to kind of figure out, okay, what do we think are stuff that's actually cyber inducible, what's not, kind of get a feel for what the actual impacts are potentially here. We kind of narrowed down to this idea of, impact and derailment of a train. Things like a switch operating while a train is over the top of it could potentially do a derailment. Collisions are pretty straightforward. Something over the track that should be preventing a switching operation doesn't lead to a collision there. As we kind of dove down to this, again, the data angle isn't something that's super important with this one. A lot of the inputs are hardwired. And as I mentioned before, this vital signal controller gets requests, not commands. So it actually makes determinations on safety. So manipulating commands from dispatch aren't really a concern from loss of safety here. So it kind of ties directly into this vital signal controller being manipulated to allow unsafe switching to occur. So once you guys identified those cyber inducible failure modes, we kind of build out these attack scenarios here. First place we usually start with this is how the control system might actually be manipulated. You kind of start with those inhibit and impair tactics on the right hand side. And then once you kind of know which systems we're concerned with, how they can be impacted, pivoting back to initial access and maneuvering through the environment to actually reach that target in question. So on that manipulate control systems perspective here, as with anything, it's always important to have an understanding of the device in question that you're concerned with. Does it run commands? Is it logic? Can you update that logic? What protections exist to prevent that updating logic? Then ask the question, what on this device can actually cause this failure here? I don't want to spend a lot of time digging through the details here. You can look at the slides later. But there's a whole host of different ways you can map those via various manipulations into the different techniques on attack for ICS here to kind of tie that together. So looking at this rail case study, again, hardwired inputs, so we're not concerned with data here. The safety is enforced at the controller, so we have to kind of identify, modifying the logic on the controller itself as the, the potential source of concern here. So we map in, modify parameters, kind of the identification for that modifying, the configuration data on the controller itself. I'll hand it back to you.
So yeah, start understanding how the system gets manipulated is really important. Another thing that's really important to start understanding is how somebody could potentially get access, right? And so when we do this, the first thing that usually comes up is like, well, let's look at the network architecture and see, what services there are and what devices connect to what and what the boundary between the OT network and the IT network is. And really understanding this technical architecture is really good and really helps identify a lot of the initial access techniques, especially like, any sort of remote services that could be leveraged or exploited, internet connected to devices, any sort of wireless communications, or maybe opportunities for rogue rogue master connections into SCADA protocols. So that's really great. And that's really like the first thing people think about. And sometimes the concern is that's like the only thing people think about too. And so that's a great place to start, but you really understand a great talk previously by Eric on the supply chain. You really understand like what's the supply chain compromise risk, right? And so that's often looking at the devices and the firmware of those devices that you should really understand for the vendors, but also the software, like the programs and the management software used to configure those. Often, sometimes that's overlooked. And then also, you know, many times you're looking at ICS device, you have an application program developed by an integrator or something like that. The supply chain of that is probably not as often as even hardened as the device side. So understanding what the programs are, you know, what are you getting from them? Are you getting just a program? Are you getting some engineering documents that have like critical values like CRCs and something in them? You know, what happens if those are tampered with, right? So really thinking broadly about what those supply chain aspects are. You know, the supply chain is important too, and you also like thinking about, you know, what do people really need? Like operations, what do the people need to actually do their job? Like, what information do they need? What communications do they need? It's not just like people down in this OT environment just working on these systems without any comms externally. Like, people need a lot of communicate. They need to look up. They need to communicate with vendors, suppliers. They need to communicate about, you know, problems they're dealing with, debugging devices, systems. So they need information. They need files and data, right? So that they need files and data to come into a system to operate it, right? And if you don't, if you just look at this static architecture, sometimes that's kind of lost, right? That what is the information people need? We see like spear phishing attachments, drive-by compromise. Those are really kind of people, you know, ways people are trying to get data from the outside to do their jobs, right? And people need that data. They might not, you know, there might be these specific two techniques might not be the only ones to cover, but thinking about what data they need and how trustworthy that data is important. And then finally, thinking about how devices are managed. So there's always the threats of like USBs or transit devices like field tech laptops, right? So in this case, you know, oftentimes a program might be transferred into the IT side and then maybe transferred to a field tech laptop and then used to connect directly to the device. And that's not in the network architecture, the static network architecture diagram. Like how people are actually interfacing with devices, what are the like equipment and such that they need to actually do the management, configuration, maintenance of this stuff day to day. Sometimes if you look into this stuff a little bit, you realize like this stuff is getting to be some shadow IT stuff that maybe is not even really well documented of what the devices and equipment that are being used to this. But you know, even if a device, sometimes people will say, well, this device is air gapped, completely air gapped. Well, it's probably not air gapped when you look at the management devices that are actually connecting to it, because you have to manage it with something and you have to get that information in. So understanding these devices is really important. And so broadly thinking about what the access is, and thinking beyond just the kind of static network architecture is important. So we'll talk about how you can manipulate the control system, how you could get access. Kind of in the same realm, you know, you could do this. You can develop this scenario. We just talked to a couple of the tactics here, but you know, there's a number of tactics in attack. You can look more broadly across those. You know, in this case, maybe there's if you do this analysis, you might realize that, you know, maybe there's an adversary could come in through like an engineering laptop or workstation, an enterprise environment. Maybe they need to access critical data, like in a file server, like some of the programs that are used for configuring these devices that aren't really considered as critical because they're not in the OT network, but they actually are really critical for the operation of the system. And then maybe they can, you know, laterally move to a field tech laptop, which is going to be then directly connected, you know, and sometime to the VLC. And once they have that, they can, you know, impair process control, modifying critical programs or parameters on that device, right? And so the idea is that, you know, by walking through this, you can develop some of these attack scenarios using the kind of TTPs we know. Even this is an example of a sector we're not really tracking with existing attacks, a lot of existing attacks in ICS, but you can really understand these same techniques could probably target other environments, could be more prepared to understand the risk of these. So once you have these a set of these attack scenarios, you know, what do you do with them? Well, one thing you can do is try to improve your mitigations or improve your resilience. The great talk this morning by Gus about really like kind of talking about how would you ensure like safety and resilience of your operations. That's like kind of, there's, you know, in attack for ICS, we have a lot of mitigations across all the techniques, right? You know, I think one thing you want to do if you're thinking about mitigations, you have these scenarios. The first thing is like, how do you prevent the impact, right? How do you prevent that operational impact? Sometimes there's like mechanical mechanisms already in play that people are not aware of, which is great. Sometimes there's, like, as Gus mentioned this morning, there's out of band data that you might know that you might not be aware of, or not be aware of how valuable it is to mitigate an attack. So understanding what data there might be, what redundancy there is, engineering more if you don't have that, making sure you have backups of like key programs and stuff like that that you need to keep the system operational. But understanding what maybe oftentimes there's, from this perspective, there's simple like auditing of system configurations and stuff like that you can do to keep the system operation, to detect some of these attacks or techniques if they did occur, right? If you understand kind of how you can ensure the safety, resiliency operations, if the next thing to do is obviously focusing on initial access. This is talked about earlier today too, like things like ensuring multi-factor authentication. These are often more the things that we commonly say are kind of more traditional cybersecurity mitigations, right? But trying to make sure that we prevent the adversary getting in is a good thing to focus on, and especially focusing on some of these systems. Everyone knows you need to worry about segmenting your OT network, but people don't often think about how to be hardening a lot of the devices that we actually use to then remotely manage and connect to these, right? And anything we can do to lock those down is going to be really helpful. And then once you kind of understand that, understanding broadly how you can the other techniques and tactics we didn't really cover here. How can we prevent really any sort of manipulation of the control system, adversary moving around the control system, stuff like network hardening, using allow lists and such like that. Obviously, these all need to be really closely tailored to your specific environment. There's not like a broad mitigation that's going to work for everyone, and it's all kind of based on where your maturity is and where your risks are. So you can use these scenarios to improve mitigations. I also think a really valuable use case of doing this is helping understand threat intelligence. And so, like a few weeks ago, when we saw the pipe dream, the in controller malware, it was really great working on Attack for ICS to see like, oh, they actually mapped all this malware to TTPs, to devices in TTPs, right, or manufacturers in TTPs, which is really great for us to see this be used like that. But I think if you're, I think it's a challenge maybe from an asset owner side to say like, okay, yeah, we have this threat info now, but do we know what to do with it? I mean, are we really prepared to handle data like this? Like, do we know what, if you're more on the security operations side, getting these threat, this threat intel, do you know like what those devices are and what functions they're used for, or how critical they are? Or is that specific technique going to be something that you find identified as like really critical to your organization or your operations? Or is this something that you actually you maybe use it in a less critical system, or it's not going to have a critical outage? And so if you kind of have gone through these scenarios, identified like which ones are most impactful to you, you can, more quickly respond and understand like, yes, this is a major risk. We know, if we see a threat to this type of device and these techniques, we know who to talk to in our organization and how we're going to respond to that. So just understanding this better from a tactics to technique level can really help more quickly responding to these types of events.
Yeah, so the question when you're building these scenarios out is always kind of like, how much is enough when you're fleshing these out? And, often the question ends up being, what's the actual application you're driving towards here? When you lay out those 3 steps, the third step there can apply across a whole bunch of different applications depending on what you're trying to focus towards. So if you're doing something like a tabletop exercise, maybe it's important to hit a breadth of different scenarios, but you don't need to flesh those scenarios out in an incredible amount of depth. The same thing with the threat intelligence one that Adam just talked about, or assessing risks across your environment broadly. You're trying to focus on a broad number of systems, kind of the key points in those. Just hitting the front end and the back end of the the scenario, where maybe you're not as concerned about the middle, fleshing that out as well. But the flip side, certain scenarios where having an incredible amount of depth in your scenarios is important here. If you're actually going to try and tailor this towards actual security testing, whether that's on the device side or testing of your environment, tying this into analytics development here in the SOC side, again having kind of the entire attack chain fleshed out is more important there. Getting down to the actual procedure level, and same thing on the mitigation side. And again, attack for ICS is focused on known adversarial TVs. So as you're fleshing this out, it's also potentially useful to think about stuff that potentially might not be included in attack because it's focusing on existing adversarial TTPs, not all possible techniques. So, kind of hitting the high notes here on what we talked about, I think there's a lot of value in kind of taking this kind of approach, kind of an adversary organizational level here, kind of helping to understand how you can apply existing techniques that you might see in other sectors, to your own environment here. I think also one of the other major benefits of this kind of approach we've seen, we've worked with other folks in their environments is kind of building that communication between security and operations, which I'm sure plenty of people have seen lackluster communications in that space. And this kind of approach is a whole bunch of different applications, depending on how you flesh out particular the details here on the mitigation side. And kind of as far as future plans here, so we're in the process of kind of work this out into a white paper here, fleshing out the case study we talked about here, as well as a couple other ones we applied it in. We've got across a couple of different verticals now, and then we're looking at ways we can take this and feed this into some other approaches here. Some we didn't talk about a lot here, but one place we did use this was take the failure scenarios that we developed for a particular environment and then build out a device testing plan based on those. So you've got these TTPs that are identified at an architectural level, and then taking that and applying that at the device level and saying, okay, what do we actually want to test against this device? Looking at ways we can better align with some of the risk assessment frameworks and mitigation frameworks here. With this approach as well, and then as always with these, always looking for ways we can partner with the community to flesh out a whole host of different MITRE frameworks and methodologies. And I think we can go ahead and hand this over to questions now.